Today I'm going to talk to you about consumption-based asset pricing and GMM type methodologies. So we might just start with a question, which is, why should we even care about consumption-based asset pricing models? I mean, after all, as students of financial economics know, the best fitting empirical models are those that explain asset returns with other asset returns. So the reason we care about these models, though, is that the true systematic risk factors are macroeconomic in nature. They're derived from the intertemporal marginal rate of substitution over some numeraire consumption good. And asset prices are derived endogenously from these. So if we want to explain why asset returns behave the way they do, we need to study these types of models. Now, some consumption-based models work better than others. And we'll start with a very basic one that doesn't fit the data very well at all, but it's a classic model. But I will emphasize here that all models are misspecified. Any model that we can dream up will be misspecified. And macro variables, which are the inputs to macro models, are often mismeasured, mismeasured more than our financial variables. So therefore, I will argue in this lecture for a movement away from specification tests of perfect fit, that is, given sampling error, the model is literally true, toward estimation and testing methodologies that recognize explicitly that all models are misspecified, and toward methods that permit a comparison of the magnitude of misspecification across multiple competing macro models. Okay, so now this is a methods lecture, so we're going to focus mostly on just the methods, but I think these themes are important in choosing which methods to use. So here's what I want to talk about today. I'm going to start with a classic example of a consumption-based model, GMM estimation of it, a representative agent model with constant relative risk aversion utility. And then talk about reduced form generalizations of this model that incorporate conditioning information in the stochastic discount factor. And I'm going to call these scale consumption-based models. And then structural form estimation of generalizations of constant relative risk aversion utility in the form of recursive utility functions like, for example, that study by Epsilon, Zinn, and Weil. And here there are two types of estimation methodologies that I will discuss, although there are others in the literature and I don't have time to talk about them, nor do I know as much about them. But one is I wrote semi-non-parametric minimum distance estimator. This abusive terminology was also called as just semi-parametric minimum distance estimator. And this would be an appropriate way to estimate these models when the law of motion for the data is left unrestricted by theory. And then I'll finish up by talking about some simulation methods, which would be an appropriate way to estimate these forms of utility functions when the theory explicitly restricts the law of motion for the data. Okay, and I'll talk about just two examples in the literature that do this in an application. Okay, and then finish up with some final thoughts about consumption-based asset pricing. So I guess we're supposed to go for an hour and a half and then have a break, and then we'll talk some more, and then at the end of that I'll try to leave 10, 15 minutes for questions if you don't mind just writing down as we go along what your questions are. That would be great. Okay, so this is a review, Hansen, 1982, GMM. Remember that this is a method of estimating theories that imply a set of moment restrictions, and that's what we see here. So you have an economic model that has some R population moment restrictions, and notice that these are unconditional means. Okay? But you have some function h, and it is over data, h by 1 vector of variables that are known at time t. Theta is an a by 1 vector of coefficients. And of course, the idea is we want to choose theta to make the sample moment as close as possible to the population moment. Okay, so that's the idea behind GMM. Now, the sample moments are just the sample analogs of the population moment. Right? So take the unconditional, take the sample mean of this h function. This is also an r by 1 vector. Y, let's stack all the observations in the sample into a vector y subscript cap t. So now we have a t times h by 1 vector of observations. And the GMM estimator is just theta hat, which minimizes this scalar. Here's this quadratic form. So choose theta to make this as small as possible. And this is just a sequence of R by R positive definite weighting matrices. Okay? It could be a function of the data. So if R is equal to A, the number of moment restrictions are the same as the number of parameters to be estimated, then you could, in principle, estimate theta just by setting each of these g's to 0. Right? So you'd have the same number of equations as unknowns. Of course, these g's are not necessarily linear, so there may not be a solution, right, to that. And we're going to talk about an example in which a very pertinent example in which that is exactly the case. There is no solution in just a minute. But if there is a solution, you would be able to find it by setting each of those to 0. So GMM refers to the use of equation 1 to weight these sample moments when we are estimating A, but the number of parameters A is less than the number of moment restrictions. Okay, so it gives us a way to weight. We have now more equations than unknowns, and we need to figure out how to weight those somehow. Right. Okay. So Hansen, of course, established the asymptotic properties of this estimator. Consistent, asymptotically normal under some assumptions, which I'll skip over here. And also established an optimal weighting matrix, so W equal to S inverse. And what does optimal mean here? It means within the class of GMM estimators, if you use this weighting matrix, you'll have the smallest variance of all GMM estimators. It doesn't mean that this GMM is asymptotically optimal, and it's not necessarily the least variance within the class of asymptotically normal estimators, but within the class of GMM estimators, it would be the smallest variance. Okay, so this S here is the spectral density matrix of frequency 0 of these H functions, right? And you will have to come up with an estimate of that, and so, obviously J can't go from negative infinity to infinity in your estimate, right? So people use things like a Newey West estimator of S, right? So you weight different J's here differently. And so usually the lags farther out get greater weight, right? And then you cut them off at some point. So you can easily find examples of these kinds of estimates of S. But what I want to talk about today is that in many asset pricing applications, it's actually not appropriate to use S inverse or an estimate of S inverse as a weighting matrix. And so we'll get into that. Okay, but keeping that in mind, if we were to do this classic Hansen GMM estimation, we would see that S depends on theta, of course, which depends on S. So the standard procedure is just to employ an iterative procedure, and you obtain some initial estimate of theta, let's call that theta 1t, right, by minimizing q. Remember, q is just the quadratic objective function, subject to some arbitrary weighting matrix. Usually people start with the identity weighting matrix. That gives you this initial estimate. Then you can plug that into the formula here, right, or your formula for the estimate, to obtain initial estimate of S, right? Re-minimize this q given your initial estimate of S and obtain a new estimate of theta. Okay, now you could continue iterating until the successive iterations between give you, arbitrarily small differences in the parameter values. Or you could stop after one iteration. And the estimators based on a single iteration have the same asymptotic distribution as the estimators based on an arbitrary number of iterations. But of course, in finite samples, these properties of these estimators will differ and may depend on the data generating process. Iterating offers the advantage that at least your estimate is invariant to the choice of initial weighting matrix and invariant to the scale of the data. Okay, so here's a classic asset pricing example that Hansen and Singleton estimated in 1982, published paper. We have a representative agent who's maximizing this utility function. Right? So C is consumption, and there's utility over. And then we have power, what's often called power utility in asset pricing, or it's an isoelastic utility function where gamma is a coefficient of relative risk aversion. If gamma is 1, there's just log utility. And if there are n assets available to be invested in, then there are n first-order conditions, which are the first-order conditions for optimal consumption choice. And these look like this. Now, this script R is just denoting the net return as a number like 5%. right? So then we add 1 to make it a gross return. And so you have they're I of these equations. Right? So here are now some moment restrictions, but there's a T here. Remember that GMM applies to unconditional moments. We have a conditional expectation here. So we'll deal with that. But let's first rewrite these moment conditions this way. So I just divided both sides. What have I done? Divide both sides by C and then subtract the 1, right? And so now I have this equation. And why is this important transformation? This is important because GMM applies to strictly stationary data. And in this moment condition, we have the level of consumption floating around. Right? But we really need we need all of these variables, all of our observations to be plausibly stationary. So it looks like the growth rate is at least much more plausibly stationary. There's a few people who would argue with that. But it's certainly more plausibly stationary than the level of consumption, which we know has important trend components in it. Okay, so we're going to rewrite the moment restriction this way. Now, here we have two parameters to be estimated, beta and gamma. And theta is our parameter vector, so it's a 2-by-1, beta and gamma. If we use X star to denote the information set that investors have in this model, then this is now our moment restriction. I'm just rewriting this explicitly conditional on this information set. And now let's take X to be an observable subset of X star. This might be something that the econometrician can observe. Right? Then this conditional model here implies the unconditional model here. So now I'm taking essentially the Kronecker product with each of these i's with X and taking the expectation of that product. Okay, so we now have transformed this into an unconditional expectation. This just follows because what's in the expectation operator here has an expectation of 0 according to the theory. So according to the theory, this whole thing should be uncorrelated with anything in X star, including some subset of stuff in X star. And so therefore this product has to be 0 in expectation. Okay, so now we have again n moment restrictions. We've turned this into a set of unconditional moment restrictions. Okay, so X can be we'll call those instruments, right? So it's m by 1. Okay, so now R, which is a set of moment restrictions that we might be taking to estimate and test on the data, is n times m. So we have n asset returns and we have m elements of X. So we have now n times m moment restrictions. And so this would be our H here. And this model can be estimated and tested as long as R is greater than or equal to 2. Right? As long as we have at least two of these guys here. So notice that we could just have X could just be 1, right? As long as we have more than at least as 2 asset returns here. All right. So let's just take the sample mean of this to get G, right? And now, of course, again, we just minimize this quadratic form and choose theta to minimize that. Right? That's our estimate of beta and gamma. And then what Hansen showed is that you can form a test of over-identifying restrictions by, it's trivial to compute once you've done the GMM. You simply take Q, which is the quadratic form here, plug in your estimate, so you take the minimized value of the objective function, multiply it times t, and that has a chi-squared distribution with degrees of freedom r minus a, asymptotically. Okay, so what does this mean to be a test of over-identifying restrictions? Well, this is a test of whether the model is actually true, right? Because it says, are our sample moments as close to 0 as we would expect them to be given sampling error? Right? So we want them to be exactly 0 if the model is correct. So that's what this is a test of. It's a test of whether the model is true. Okay. So by the way, this test holds, I should have said, for that test to be true, you need this weighting matrix to be the S inverse, though. Okay, it can't just be any arbitrary thing, right? Then this test holds. You can form other versions of this test when the weighting matrix isn't S inverse, but it doesn't have quite this simple form. Okay. Now, Hansen and Singleton, took this to the data and estimated this model, and they used lags of consumption growth and returns for their X. Right? So they didn't just have ones, they had some variables in there. And for the asset returns, they had a broad stock market index and then some portfolio industry returns, so returns of stocks over various industries. And they use non-durables and services expenditures for consumption growth. This is fairly standard, right, in consumption-based literature, at least testing representative agent models. Okay? So that was their data, and they had some estimates here. The beta looks, subjective time discount factor looks fairly okay, close to somewhere around 0.99 across their various estimates. Risk aversion was estimated to be low, 0.33 to like 1, essentially. So there's no equity premium puzzle here. I'll say why that is in just a moment. But the model was strongly rejected according to these kinds of over-identifying restrictions. Okay. So then later on in Campbell, Lowe, and McKinley, if you look at that book, they report results. Or they don't actually have a table, but they say in the book, and I know this to be true from playing around with this stuff myself, that these over-identifying restrictions were rejected in their paper, but they're much more strongly rejected if the set of test assets includes both equity returns and some type of commercial paper rate or short-term interest rate, like a treasury bill rate. Okay. And why is that? Well, that's because this model with these preferences cannot capture the predictable variation in excess returns over commercial paper or over a short-term treasury rate. Okay, and because, so if you think about what's happening here, E of m times r minus 1 has to be 0. So if r is moving around in a predictable way, and m is not moving just covariating just the right way, then E of m times r is not going to be equal to 1. And that's exactly what happens here. So this has led researchers to turn to other model preferences, actually, because this is a very strong rejection of the power utility model, the constant relative risk aversion model. This kind of predictability in excess returns in this model, you might think, well, that might be explained by heteroscedasticity and consumption growth, right? Or it might be explained by time-varying covariances between consumption growth and returns, right? Because that would generate in the model some predictability in excess returns. In fact, GMM is a distribution-free estimation procedure, right? So it would allow for that kind of heteroscedasticity. And if that could then explain this kind of predictability, it shouldn't have led to strong rejections of the model, and even stronger rejections that occur when these excess returns are included. So it is for this reason that many researchers said, well, we need to abandon this entire set of preferences. There must be something wrong with that. Okay. All right, so now notice that Hansen and Singleton did use some conditioning information. Their X was not just a vector of 1s, as I said. So this is like what I'll call scaled returns. Okay, so instead of, if we go way back here, yeah. So look at these moment conditions. This is a gross return. It's as if this were just a vector of 1s, you start out with some equity return right here. Now you're multiplying it by x. Now you're looking at a different set of asset returns. You're no longer just looking at the equity return. You're looking at the equity return times x, right? So this turns out to be the reason why they don't have an equity premium puzzle, because we're no longer trying to explain the excess returns on the stock market, right? We're taking that and multiplying by x. Okay, so which moments you're actually using to test will bring out different puzzles with this model, but that was not the puzzle that came out here with these so-called scaled returns. I'm going to talk about scaled returns more a little later. But another limitation with the classic consumption cap M is the large unconditional Euler equation error. So now let's go back to thinking about x just being 1, for example, or let's call these pricing errors, even when these parameters are freely chosen to fit the data. Okay, so what do I mean by that? Suppose we just take M. The M is, I'm calling M a bunch of things. M is the intertemporal marginal rate of substitution over consumption. M is the stochastic discount factor, and sometimes I'll call it the pricing kernel. Okay, but it's always this kind of thing. Right? So now if we define Euler equation errors, or pricing errors, for the case of raw returns, that would be this. There's no T here, so these are unconditional. Right? And excess returns, the error would be this. If the model is true, those should be 0. Right? And then let's use GMM to choose parameters beta and gamma. There's 2 parameters here. So this is, again, just the G, or the sample means of these errors, right? This is just as we've been talking about.
And W can be anything for this result. I mean, you can use the optimal weighting matrix, you could use the identity. This result doesn't depend on that. But now let's just plot, take for this model, use post-war data from 54 to 2002, and let's plot what these errors are as a function of gamma. Okay, these are for the excess return. So here there's only one. So we have two sets of asset returns here. One is just a stock market return. So we have one parameter. Beta is set, it says down here, in order to minimize the Euler equation for the T-bill. Right? But so now we're just choosing gamma to make this excess return error as small as possible. And to give a sense of how large this error is relative to the assets being priced, we're going to plot the root mean squared Euler equation error relative to the root mean squared return, which is just the sum of the square root of the average square returns of the assets being priced. So here there's just, these lines are almost on top of each other. There's one line for the stock market return, Chris value weighted index, and then another is a multiple set of returns. So we have the stock market return in these 6 portfolios sorted on the basis, 2 on the basis of market capitalization, high and low, and then 3 on the basis of book to market ratio. So we have sort of a portfolio of stock returns. Well, what this says is that the root mean square error can never be driven anywhere near to 0, no matter what gamma is. In fact, the smallest it can be is around, gamma is like 112 here. Right? It's about 60% of the average square returns on the assets being priced. So for the single stock market return, this is just saying that the Euler equation error is 60% of the average annual stock market return. So that's really big. And this model is not anywhere near as being able to capture that. So this is a very large magnitude of error. And unlike the equity premium puzzle, these large Euler equation errors cannot be resolved with high risk aversion. Now, we took some leading consumption-based asset pricing models, including habit-based models that have done very well in other, matching other aspects of asset pricing data, like Campbell and Cochran model, and the variant of that studied by Mensley, Santos, and Veronese. Long-run risk models that have also become very popular. We'll talk about estimating one of those in a minute. And limited participation model studied by Guvnin. And we asked whether those models could explain the failure of the standard model in this dimension. Right? And none of them could. In other words, if those models really did generate the data, then what you would find is that if you took that data and did GMM estimation of the standard constant relative risk aversion consumption-based model, you would always be able to find values of beta and gamma such that the Euler equation for that constant relative risk aversion model were exactly satisfied, whereas that's not true in the data. So in this world, these models are implying that an observationally equivalent model for a different set of parameters, it would just be the standard classic model. That should work perfectly well. Okay, now we found this to be a striking anomaly, actually, because much of the early evidence, like the Hansen and Singleton evidence, that the classic models' Euler equation errors Euler equations were violated, provided a lot of the impetus for developing these newer models in the first place. So that's still, what this means is that the data on consumption and asset returns are not jointly log normal, and almost all of these models, they're approximately jointly log normal, if not exactly. So, okay, so, yeah?
Cindy, is it okay to ask a question?
Well, Jim, you may have missed, he requested the questions be left in the last 15 minutes
I came in late.
because we're video recording. But if you don't mind. Okay. So now we talked about using non-optimal weighting matrices in GMM. And what I want to talk about now is reasons why in asset pricing applications we often don't want to use the optimal GMM weighting matrix. And why is that? So here's a bunch of different reasons. Okay. They may vary from application to application. One reason is that assessing specification error and comparing models. So suppose we have two estimated models of the SDF. Right? So one may be the classic consumption-based model. Right?
OID restrictions are not rejected. Suppose they weren't rejected. And then say the CAPM, which is just a simple linear model where this is the returned aggregate wealth, or all invested wealth. Okay. Now, here you might find that the OID restrictions are rejected if you do this Hansen optimal weighting matrix and test the over-identifying restrictions. So are we right to conclude that model 1 is better than model 2? Well, no, because this J test depends on a model-specific S. So it's as if you're comparing apples to oranges. And what can happen here is that model 1 could look better than model 2 simply because the stochastic discount factor and the pricing errors make G more volatile. So they're more volatile, they make G more volatile. And that's just blowing up the variance of everything, right? It's making it harder to detect deviations from 0 in these sample means, right? But it's not because their pricing errors are lower, right? So this one could actually have much lower pricing errors and not be rejected if it's better measured, right? The M is better measured. So we can't really, if you want to compare models, you can't do that this way. So the classic way to do that is based on work by Hansen, Jagannathan. If you want to compare models, the idea is, let's say you have a candidate stochastic discount factor that's a function of parameters. And you're going to use this distance metric, where this is, again, just a square root of a GMM criterion function, where you're using a specific weighting matrix. This is G. G is the second moment matrix for returns. And again, this is just the same thing we've been estimating, sample mean here of M times R minus 1. Notice that this distance metric does not reward stochastic discount factor volatility. In other words, G is the same for all models. Right? So now you're putting them on equal playing field. And so it's suitable for model comparison, plus this distance metric is a measure of model misspecification. All right? And two ways to think about that, as they show. It gives the distance between the candidate stochastic discount factor and the nearest point to it in the space of all stochastic discount factors that price assets correctly. And it gives the maximum pricing error per unit norm of any portfolio formed on these N assets. So now we have a metric. It's suitable for model comparison, and it's a measure of this extent of misspecification of the model. Okay? And that's really one of the great appeals of this distance metrics. Recognizes that all models are misspecified and gives us a measure of how much each model is misspecified, and provides a method for comparing models by assessing which model is least misspecified. Now, an important problem, though, is how to compare these HJ distances statistically. 8:45. Just want to see. So I'm supposed to stop at what time for break? 10? What does it say? Sorry. 10 what? 10:15 I stop? What time is it now? 9:15. Okay. So an important problem then is, well, how would we think about comparing HJ distances statistically? All right, so we can now compute HJ distances and see that model A has a different one from model B, but how different is model A's from model B? And in much of the literature, we only know how to test, we have results for knowing how to test whether model A's distance is itself different from 0 and model B's is different from 0. That doesn't tell us how different they are from one another. So one possibility that Xiaohong Chen and I worked on recently is to use a method based on White's reality check. And this method allows one to compare statistically HJ distances among K, some number, finite number of competing models using White's reality check method. So here's this method. And let's just take, what you do is you take your benchmark. So now you've estimated HJ distances for a bunch of models. Right? And you can rank them by distance or square distance. I'll explain in a moment why we use square distances here. But so now you've ranked these by squared distances. And let's just take your favorite model. Let's say usually it would be the one with the smallest square distance. Right? And the question is that
the smallest statistically from the others. Okay? So now, the null then would be that the squared distance on model 1 is smaller than the squared distance on a second model, where the D2 here is the competing model with the next smallest squared distance. Okay, so now you're going to form a test statistic, the script TW, which is root T times just the difference in these distances. And if the intuition here is if the null is true, right, the test statistic should not be unusually large, given sampling error. Okay. So now, if you had a distribution for tau w, you would simply, it's a one-sided test, so you'd simply reject the null if the historical value of this test statistic, which you can easily compute given that you've computed squared distances or distances for each of these models, that has to be, if that's greater than the 95th percentile, you would reject the null. But it's less, you wouldn't. Okay, so the appeal of this method is that it applies generally to any stationary law of motion for the data. There have been a few methods. One that I know of that was developed for VAR specifications with Gaussian errors, but this doesn't require that, just stationary law of motion for the data. And to multiple competing models that are possibly nonlinear. Right? It doesn't have to be a linear stochastic discount factor. So it's actually quite general. What about the distribution? Well, the distribution of tau in practice is computed via a block bootstrap. That might be time-consuming if you have a highly nonlinear model, but it's in principle straightforward. And the reason is because tau w has a complicated limiting distribution, so it's actually just easier to compute it via block bootstrap. But of course, the bootstrap isn't justified unless we know, theoretically, that we have a multivariate joint continuous limiting distribution under the null. Okay? Well, fortunately, we know that, or at least we have proofs of that, for applications that are relevant to most asset pricing models. Okay, so for parametric models, we know that from results in Hansen, Heaton, and Lutmer. And for semi-parametric models, which we'll talk about later, which include an unknown function, right, we have results in I and Chen. Okay, so this is a very general methodology that can be used to compare distance metrics across models. All right, why else do we use non-optimal weighting? Well, there are other potential reasons. Here are some reasons that we might just want to use the identity matrix. You have the econometric problems, near singular S inverse or G inverse. So, it's just that asset returns are highly correlated, right? So if you have large N and a modest T, and we can have many, many asset returns, right? If we were to look at the universe of stocks, for example, that would be a very large number, and then our time series dimension isn't necessarily that large. So if T is less than N, the covariance matrix for the N asset returns is singular. We can't invert that at all. Well, if T isn't sufficiently larger than N, then this matrix can be near singular, and this can be poorly conditioned, and you run into all sorts of problems. There was a whole issue of the JPES about 1996 or so that studied the finite sample problems of GMM, and most of them revolve around poorly conditioned values of this S and G in finite samples. Okay, so get rid of that and just use I, and sometimes that's more stable. The other reason that people may want to use the identity weighting matrix in asset pricing applications is that the original test assets that you use have often been carefully chosen to represent particular economic characteristics such as size and value. Now, if you come along and use a weighting matrix like S inverse or G inverse, you're sort of undoing that. An easy way to see that is just to note that if you use one of these weighting matrices, that's the same as using the identity weighting matrix and then doing GMM on a reweighted portfolio of the original test assets. Okay, so now you're no longer testing anything on the original test assets. You've moved on to some other. And that's just easy to see by noting that a positive semi-definite matrix is a factorization. It looks like this, so I can write this like this. Right? So this is the same objective function, but this is now the identity weighting. If you write out the elements of this, you see that what you're really doing is GMM with a different set of portfolios now, returns, not the original set of assets. The other thing is that these reweighted portfolios may not provide a very large spread in average returns. I mean, they could, it depends. You're choosing this weighting in some statistically optimal way, but now you don't know what you're getting in the end. And that means there's less for the model to test. I mean, these are cross-sectional asset pricing models, and we're ultimately testing whether the covariance between the stochastic discount factor and the gross return is enough to explain the spread in average returns on these assets. Right? So now if we don't have a large spread, there's not as much for the model to test. Could also be this reweighting implies that these portfolios look kind of crazy. They might imply implausible long and short positions in the original test assets. Okay, but here's a reason not to use I. So as in so many things in applied work, there's judgment that comes into play about what you actually are trying to achieve. But if you use let's say use the second moment matrix of returns as a weighting matrix, then the GMM objective function is invariant to the choice of test assets, at least the initial choice, to the extent that the set of assets out there can be spanned by the set that you have, if it's rich enough. Then now this will make your estimate invariant to the choice of test assets that you have. And that's kind of a nice feature. And that's easy to see by just form a portfolio A times R from the initial asset returns R. Okay. So R is n by 1 and A is n by n. Now we've got different portfolio of linear combinations of these R's. Okay. Now notice that these weights sum to 1, so A times a vector of 1s is just back to a vector of 1s. Okay. But now I can simply rewrite this. This is what we would estimate on the original set of test assets if we used the second moment matrix inverse as a way of weighting the GMM objective function as suggested by Hansen and Jagannathan. We can rewrite that, and that's the same as this. So objective function is invariant to any portfolio transformation of the original test assets. Okay. So, of course, with W equal I, that will not be true. Your GMM objective function will depend on that. Again, you may want that if you're very interested in testing whether the model can explain those aspects of that particular set of asset returns. But you may not want that. Depends on the application. Okay, so let's talk a little bit about some generalizations of the standard model. As I said before, people have moved away from these preferences because they don't seem to match the data very well. And it doesn't seem like just patching it up with some heteroscedasticity and consumption growth and with these preferences is going to fix things. So people have started looking at other preferences. Now, many consumption-based models can be approximated in reduced form as a linear function of consumption growth. This is now lowercase letters or log variables. Okay. A simple example is back to our old classic model, consumption cap M. And then these weights here, A and B, are fixed. Right? This is just a fixed parameters depending on beta and gamma. Right? Okay. But you can look at more complicated models, okay, and with habit formation. So, for example, with Campbell and Cochran, or Mensley et al., they have a habit formation model that depends on some parameters here. Right? So now X is a habit, and your utility depends on C minus X, right? Not just on C. And so they call this a surplus consumption ratio. So what we see happening here is that the log surplus consumption ratio ends up here. And these are just nonlinear functions that are part of their model, these psi's and gammas. Okay. Okay, and just actually any habit-based model could fall into this category, right? You could approximate it will look something like this. Okay. So Fersen and Constantinides estimate something, but they don't use this reduced form, but they also have a simple habit structure, and will be approximated. It will look something like this. Okay. Now, In this model, the A and the B move around with the surplus consumption ratio, and in this model, the surplus consumption ratio moves around risk aversion. So risk premia are moving with S. Okay? So now we have a situation where M should depend on A and B in a way that, you know, proxies for time-varying risk premia should be good proxies for time variation in A and B. Okay, so with that in mind, you know, we could think of various empirical specifications. Martin Letow and I looked at one where we said, well, let's just let A and B be linear functions of some Z. And Z is a CAY thing, which is a co-integrating residual between consumption, asset wealth, and labor income. And, you know, it's related to the log consumption aggregate wealth ratio, but it also is a strong predictor of excess stock market returns. So this is what we would consider a proxy for risk premia moving around over time. Okay, so you're thinking of putting forecasting variables for excess returns in there. Right? So this is very reduced form because this is not necessarily a structural estimation by any stretch. Right? But yet it differs from the standard model in that we have this state-dependent weights here. So the pricing kernel is now a state-dependent function of consumption growth. Other examples, you know, so almost any model can be approximated this way. Take housing, you know, take a model that has two elements, two arguments in the utility function. So you have some housing consumption, some numeraire non-housing consumption. And then this is just a CES aggregator over those two, and then you have a constant relative risk aversion over the aggregate. Now, the log of M could be approximated this way. So now you have time-varying weights potentially here, right? And this S is just the numeraire, it's the relative share of numeraire consumption and total consumption. Right? So these are relative prices here, 1, 2, 3. Okay, so look, for example, Lustig and Van Nieuwenburg have a paper. They have some incomplete markets model. And because of incomplete markets, there's imperfect risk sharing. And one of the ways that you can insure against idiosyncratic shocks in this model is you could borrow, but how much you can borrow depends on how much collateral you have, housing collateral. So the value of housing determines how much you can borrow. So in the aggregate, of course, that amount of housing collateral varies with the price of the house. That's endogenous in their model. But you can imagine that the housing collateral ratio to what? It's the amount of housing collateral relative to something, say the amount of housing wealth. The amount of, not wealth, forget now what's the ratio, but think of the amount of housing collateral. As that goes up, there's more risk sharing because people can insure against risks now more. Right? They can borrow more and insure against risks. So risk premium should go down. So in their specification, the amount of housing collateral is what's in Z. Okay? And they take this to the data as well. So their Z is a function of housing collateral. Right? So here, risk premium move around not because risk aversion is moving around, but because the quantity of risk that can be shared or insured against changes over time with the housing collateral. Okay, so at this point, it's important to point out that there's two kinds of conditioning information, conditioning that is often confused. Think about the Euler equation. We have Euler equation often looks like this, right? So it's a conditional mean here, a conditional on some z, right? There's an unconditional version, which is just, you know, take unconditional expectations of both sides, and now we have this, right? Okay, so it's conditioned down to unconditional expectations by the law of iterated expectations. That second bullet point holds from the first. Now, there's two forms of conditionality. One is what I referred to earlier as scaled returns, and that's a way of capturing this kind of conditioning information, right? So you take the return. This is now a gross return, 1 plus that script R. Right? You take the return here, you chronicle it with a set of instruments, 1 and it could be constant, right, and then some Z. And then the other is you scale factors, and that's what I've just been talking about in the previous two slides. Okay, so some set of factors, so say you have start out with some fundamental factor like consumption growth, and now suggests that M, the pricing kernel, the stochastic discount factor, is a linear function of that with potentially time-varying weights. Right? That's what we've just been talking about. Okay, so scaling factors looks like this, right? Which is different from scaling returns. Now, the scale consumption-based models that people have looked at are conditional in the sense that M itself is a state-dependent function of consumption growth, which is not true of the classic model. And so that means factors are scaled. These scale consumption-based models have been tested, however, on unconditional moments, that is, testing the model's unconditional implications, not the conditional implications, so that we're not scaling returns here. So there's no conditioning going on here. So what this means is scale consumption CAP-M models turn a single factor model with one fundamental factor, which is consumption growth, into a single factor model with state-dependent weights into a multi-factor model with constant weights. And I think I'm using now F for multiple factors, which is a little confusing. But M, we write like this, for example, right? Now we've turned a single factor model with state-dependent weights into a multiple factor model. We have factor 1, factor 2, factor 3, which is the product of Z in next period's consumption growth. So we're back to, now we have a multiple factor model. Let's just call these multiple factors F now in a vector. We no longer have a single consumption factor. And so now we're going to have multiple constant betas for each factor rather than a single time-varying beta for consumption growth. So it's not a conditional consumption CAP-M in the sense that there's a single time-varying consumption. No, there's just more than one constant beta. Okay. This just shows you how to derive the beta representation. Okay. Just ignore time indices and let F be F prime stacked with 1, and then M is a linear function of F, right? So we start with this set of moment restrictions. These are Euler equations. Right? R times F prime times B is just plugging in this to here, right? Keep in mind these are unconditional moments. There's no T here. We're testing the model on the unconditional implications. So if you write that out like this, right, you just use the definition of covariance. Right? You write that out like this, then you can show that the expected return on each asset is a function of this, and then rewriting things. What is B bar? That might be a typo. I'm not sure what B bar is. I think that's a typo. It's not coming to me now, but this line seems to be the same as that if B bar is just B. In any case, at the end of the day, you end up with something that looks like this, right? You can rewrite it so things look like this. Now, what is this piece here? Right? That's the beta. It's a multiple regression coefficient of returns on factors. Right? That's beta. This piece here is like lambda, something sometimes called the price of risk. And notice that we now have multiple constant betas. Right? So we have multiple sources of price risk. And you can estimate this in a cross-sectional model using the Feldman-Macbeth methodology, and Michael Brandt is going to talk about that. So I won't say much about it, but here's just a preview of what you do. You would estimate these betas in a first pass time series regression. Okay, so beta I is just, these are just multiple regression coefficients. Returns on factors, right, for each return. And then second, you have T cross-sectional regressions, one for each period in your sample. Right, so you're going to regress excess returns. This would be some reference return, maybe a T-bill or something in practice, on these betas, and you're going to store each time you get a different lambda and a different alpha. Okay, and then you just take the average of those as your estimate of lambda. Right, and you would do the same for your estimate of alpha. This would be a pricing error. This should be 0 if the model's true. You could test where this pricing error is 0, but then, right? So then this would be the variance of your estimated lambda. Okay, and then you would want to report t statistics that are corrected for the fact that you've estimated the beta in the first stage. Right? Okay, so Michael Brandt will tell you more about that. But here the point is that these scaled models, the conditioning is done in the SDF. Okay, so now we've turned a model that's a state-independent function of consumption growth into one that's a state-dependent function of consumption growth, but not in the Euler equation. And this could give rise to a restricted conditional consumption beta model, so that notice that now that we have multiple factors, 1, 2, 3, we've got 3 betas here, right? We could rewrite this way, and we could call this a time-varying consumption beta. And we could look at the properties of that. But notice that this is not what you would necessarily get from estimating a time-varying consumption beta by modeling time variation in this particular conditional mean. Right? It's unlikely to be the same. And notice also that you have to control here for an additional risk factor, or a lagged risk factor. And this is going to move around with some proxy for risk premium. Okay. Now, why am I making such a big deal out of this distinction? Well, it's important because with conditioning in the stochastic discount factor, theory often provides guidance about what kinds of variables you'd want to put in there. These weights move around with some proxies for risk premium usually. Okay, so if you have a handful of good predictor variables for returns, you could think about using those. Right? That's really what you would, typically a few variables that capture risk premia should enter if you're estimating one of these reduced form models. But if you have conditioning in the Euler equation, you now have to model the entire joint distribution of M and R. Right? This could require many variables beyond that, just a few which capture risk premia. So we're trying to model the conditional expectation of M and R. In principle, that means you have to take M and R, take the expectation of that times every variable that's in the investor information set, right, that you're conditioning on, and every nonlinear transformation of that. Right? That's in principle what the conditional mean of that is. So that could be an awful lot of instruments in a finite sample. And in practice, the results could be quite sensitive to your chosen conditioning variables. These variables may fail to span the information set of market participants. Okay, so suppose you go out and you try to test ET of M times R equals 1 for some model M, and you put in some conditioning variables, X, in there to capture the... Yeah, you might not find that the model works so well. Well, it's not clear. What you've really found, maybe it's conditional on those variables. Maybe you haven't included enough conditioning variables. There's lots of information out there investors might be conditioning on. Maybe you don't have enough nonlinear functions of these variables in there, and you're just not approximating the conditional expectation well enough. Okay? So we don't know. The one partial solution is to attempt to deal with this by summarizing the information in a large number of time series with a few estimated factors, dynamic factors. So I've done this in a couple of papers with Serena Eng, and I don't really have time to talk about that today, but you could take hundreds or potentially even thousands of economic time series and estimate a small number of factors, and you can test statistically for how many those should be, and summarize the information in all those hundreds of time series. So bottom line here, we have some conditional moments of M times R. Those are potentially very difficult to model, right? Because we don't necessarily know whether we have a rich enough information set that we've relied on. And this is a reason to focus on unconditional moments, a reason to focus on these moments, right, in testing models. Second is that these models are all misspecified, right?
They're not correct. And the interesting question to me is whether the state dependence of M on consumption growth implies less misspecification than the standard fixed weight consumption cap M. The interesting question is not whether the scaled model or any other model is literally true, because I don't think they are. And as before, we could compare these models on the basis of HJ distances and use this white reality check method to compare them statistically. So we can really get at the question of, okay, given that these are all misspecified, which is least misspecified of the set of models? Now I want to talk about generalizations of the constant relative risk aversion model, but generalizations that we're no longer going to be thinking about reduced form generalizations, approximate linear state-dependent functions of consumption growth, but instead estimating the actual structural form of a particular generalization with recursive preferences, and that one studied by Epsilons and Weil. Okay, so this is kind of recursive utility is of interest because one is that it affords a far more greater degree of flexibility as regards attitudes towards risk and intertemporal substitution than does the standard constant relative risk aversion model. So this flexibility is of interest often because it's unclear why an agent's willingness to substitute consumption across random states of nature should be so closely tied to her willingness to substitute consumption deterministically over time, as it is in our old friend, the constant relative risk aversion classic consumption cap M model. Right? Those two are very closely related. So risk aversion, the coefficient of risk aversion is the inverse of the elasticity of intertemporal substitution in that model. And secondly, because these preferences deliver an added risk factor for explaining asset returns above and beyond the risk factor in the standard consumption-based asset pricing model with constant relative risk aversion utility. So we'll see that. Now that's good because that model doesn't seem to have the right kind of risk or enough risk factors or something to explain the spread and risk premium that we observe in asset return data. But there's really been just a small amount of econometric work, at least estimating structural models of recursive preferences. Okay, so there's two papers I'm going to talk about, but this is, these are only starts, and there's this gap in the literature. Actually, there's an entire gap of structural estimation in the literature, in my view. But part of the reason is that these are complicated models to estimate structurally. Okay, so I wanted to discuss here two examples of estimating Epsilons and Weil models. Right? Okay, so for general stationary consumption growth and cash flow dynamics, we're not going to restrict that law of motion. I'm going to talk about some work I've done with Xiaohong Chen and Jack Fabalukas. And then when restricting cash flow dynamics, that is when the cash flow dynamics are explicitly part of the model, such in the Bonzal-Yaron style long-run risk models. I'm going to talk about some paper by Bonzal, Gallant, and Tauken, which estimates this model. And so in the first case, the data generating process is left unrestricted, and as is the joint distribution of consumption and asset returns. So this is a distribution-free estimation procedure, a lot like GMM. So it ties back into our theme of GMM. And in the second case, both the data generating process and the distribution of shocks are explicitly modeled. They're part of the theory. Right? You exploit that in estimation. Okay. So here's some basics from this model. We have V. Right, what is V? V is the utility function. This is the recursive utility function. We're going to just focus on the specific case that Epsilons and Weil studied. Okay, this is just one version of recursive utility, right, where you have the CES aggregator over consumption, right, and V is the continuation value of the future consumption plan. Right? And R is this
nonlinear function of that, and this script f is the information set upon which investors are conditioning expectations. All right, so theta is, let's go back here. Theta is a relative risk aversion measure, and 1 over rho is a measure of the elasticity of intertemporal substitution. And beta, again, is a subjective time discount factor. Okay, so this is the way the utility function works. Now we're going to be estimating an Euler equation that uses this, right? So we need to, all of our estimation methodologies, almost all of them require stationary data. So we sort of need to transform everything so that we're using plausibly stationary variables. So we're going to divide by C, right? And now we're going to have a formula for V over C, right? Instead of just V. Just divide everything by C. Right? And that's what you end up with. So Hansen, Heaton, and Lee did this in a recent paper. Right? They worked with this form of the utility function. Okay, so a special case, of course, is when rho is theta, and then you collapse right back to the constant relative risk aversion separable utility model with V equal to beta times C. This is just the power utility model again. So switching notation. So now theta is what gamma was before. Okay. All right, so the marginal rate of substitution here is the pricing kernel with the added risk factor. And what do I mean by that? So here we have this, looks a lot like, and in fact is, exactly what our old friend, the classic consumption cap M had. Right? This would get rid of this, and you end up with just this, and this would be your stochastic discount factor. Right? But now we have this whole multiplicative term here, and you can see how this really expands the scope of the asset pricing implications, potentially, in the right direction. Because now, I mean, the question of whether a model explains asset returns is really the question of whether the M covaries with gross returns in the right way. Right? Because E of M times R minus 1 must be 0. So discounted returns are always the same for every asset. They have to be in expectation equal to 1, right? And that's what the model implies. So if the model is going to do well, and then each asset has its own unique covariance with M, and that's why we get different risk premium. So M has to move around in the right way. So you can imagine that if this doesn't move around, well, maybe this stuff, which depends on the continuation value of the future consumption plan, does move around in the right way. So there's some scope for help here with this model. Okay, so obviously a difficulty that we face in thinking about estimating models that have this structure is that we see that this, first of all, there's this unobservable in general continuate. In general, we don't know what this V over C is. We don't know what V is. This is an unobservable function of future consumption. And it embeds this script R, which has an expectation of, it's a nonlinear function of an expectation. That's also tricky to deal with in estimation. And I think about GMM, that would be a problem. You can just apply GMM. We'll see that in a minute. Okay, so one approach to this problem in practical applications that was used by Epstein and Zinn, right, in an empirical paper, is to say, well, look, we could derive an alternative representation of M in which we relate the continuation value of the future consumption plan to the return to all invested wealth, or to aggregate wealth. And if we do that, we could rewrite the stochastic discount factor this way. So now we have this piece, which looks like the standard piece, raise it to some power, but we have now 1 over RW, where RW is the aggregate wealth return. Okay. And in this application, what did they do? They said, well, this is straightforward. If we had data on RW, we could just take it, this model, and estimate by GMM, just the way we've been talking about. Instead of having this piece be RM, we'd have the whole thing. So we just need data on RW. So So what did they do? They said, well, let's take the aggregate stock market return and use that as a proxy for RW. Plug that in, proceed with GMM. So that's a really reasonable place to start, and you might try a few different observable returns. The problem with that, of course, is that RW represents a claim to future consumption. That's itself unobservable. And there are lots of parts of aggregate wealth that, for example, human capital, that we don't observe the return to. Many estimates suggest that human capital is the largest component by a large fraction of human wealth, and that actually stock market wealth is very small. So we might be a little concerned that we're not adequately proxying this unobservable aggregate wealth return. In essence, we haven't really solved the problem of having the unobservable V by doing this, right? Because RW is no more observable than V. Okay, so there's some special cases, however, that will make this problem go away, this unobservability of V or RW. So for example, make this model more tractable. Right? So one is that the EIS is 1, suppose, and log consumption growth follows, let's just say linear time series process. So this is log linear. Then the log of V over C does have an analytical solution. And actually, this is what Hansen, Heaton, and Lee exploited. There's another paper. Hansen, Heaton, and Lee used aggregate data. This is a paper in 2005, JPE. And then Malloy, Moskowitz, and Bissing-Jorgensen used disaggregated data and stock market holder consumption data based on Annette Bissing-Jorgensen's work, measuring the consumption of stockholders. Okay. And so now that once you have a solution, analytical solution for V over C as a function of future consumption, you can just proceed to estimate, right, in that case. Okay, but you need the EIS to be 1, and you need this assumption to be true. If returns and consumption are assumed to be jointly log normal and homoscedastic, then you can show that risk premia are an approximate log linear function of the covariance between returns and news about current and future consumption growth. So now, if this were the assumptions that you were making, all you would need is a model of expectations, multiple steps in the future in order to compute these news terms, right? That's easy to do from a VAR, right? That's what people like Campbell have worked on estimating models where they've made these approximations. And then you obtain a cross-sectional asset pricing model where you have a bunch of excess returns and they're functions of these covariances of returns in these news terms about future consumption growth. Okay, but of course, these are all special cases. And the EIS equal to 1 implies the consumption wealth ratio is constant. It seems to contradict statistical evidence that it's not. Well, you might ask about what statistical evidence, since aggregate wealth isn't observable. So we don't know for sure that it's not, but for example, the co-integrating residual between consumption, asset wealth, and labor income should be highly correlated, if not perfectly correlated, depending on some assumptions you make about the statistical properties of labor income with the consumption wealth ratio. And that then would move around expected returns, and in the data, at least the observable component of that, this co-integrating residual does forecast expected returns. So this is highly suggestive. The consumption wealth ratio is not constant over time. But also joint log normality of consumption and asset returns is strongly rejected in the data. So we talked about one aspect of that earlier, right, which is that there's no, you take a single excess return, right, you have now, for any parameter gamma, you can never drive the Euler equation to 0. Right? That would say that the joint distribution, that would be true, back up. If consumption and asset returns were jointly log normal, you would always be able to find a gamma that made that excess return 0. Right? Because essentially you end up with a log linear specification, 2 linear equations and 2 unknowns, beta and gamma, and you can solve that. So this says that the consumption and asset return data are not jointly log normal, and indeed statistical tests strongly reject joint log normality. Consumption growth itself looks pretty log normal in a univariate way, but not the joint distribution of consumption and asset returns. Okay. All right, well, these considerations to us point for the need for estimation methodologies that are feasible under less restrictive assumptions. So we'd like to be able to estimate this model and say something about its parameters and how well it fits the data, okay, without making these kinds of approximations, although these are very good first steps. Okay, so now, and we don't necessarily want to make these approximations. We'd like to be able to evaluate the model against asset pricing data, and we don't want to make these approximations. Because without doing so, we don't really know how well these models fit the data once we've relaxed these assumptions. Okay. And we don't know that for sure that these assumptions are innocuous, right, for reasons that we just discussed. So, keep in mind, here we are with, this is this pricing kernel that we're dealing with here. And remember that this script R is a function of, here, it's a nonlinear function of a conditional expectation of the continuation value of the future consumption plan. And we're going to write it like this, actually. So we're functions of stationary variables. Okay, so that's the goal. So what I'm first going to talk about is some work that I've done recently with Xiaohong Chen and Jack Pavloukas, in which we use a semi-parametric approach to estimate this model. And we do not need to proxy for the unobservable aggregate wealth return. So we're not looking out there to find a proxy for this. We don't need to log linearize the model, as in some of these previous approximations. And we're not going to place parametric restrictions on either the law of motion for the data or the joint distribution of consumption and asset returns or the value of key preference parameters such as the elasticity of intertemporal substitution. Okay, so the goal here is to be as general as possible. And then what can we do? Well, we can obtain estimates of the structural parameters of the model, beta, relative risk aversion theta, the inverse of the EIS. Once we have those estimates, we can evaluate how well this model fits the data relative to competing specifications. And then we could investigate the implications for the aggregate wealth return and for the return to human wealth if we're willing to make some assumptions about the relationship between aggregate wealth and human wealth and stock market wealth. So for example, in this work, we will assume that the aggregate wealth return is a portfolio weighted average of the return to human capital and the return to stock market wealth. Okay, well, that's an assumption. Okay, so this semi-parametric approach is an example of a sieve minimum distance procedure. Okay, so we'll talk about what that is. Okay, so let's go back to our first order conditions. So here's the first order condition for optimal consumption choice in the Epstein-Zinn-Weil model. Okay, and again, you've got this script R embedded in here. Now notice that in this general state, right, you couldn't just take this to the data and do GMM. In other words, you're not going to like Kronecker this with X, where X is some known conditioning variables, and go off and do GMM. Why? Well, because this script R embeds an expectation. So for GMM, you have to have the expectation all on the outside. Okay, so we have a problem doing GMM. There are other problems doing GMM here. I mean, the other problem is we don't have data on V, so we can't just go to town like that. Okay, so first of all, what you can do is recall that the definition of the utility function scaled by consumption is this. Right. So now let's take that definition, substitute in for this script R, right? Invert that, substitute in here, and write it like that. Okay, so now we have n moment restrictions. And these are Euler equations. Okay, so if you have n test asset returns, you've got n moment restrictions. And then this is a cross-sectional asset pricing model. Right? So it says that, we're going to explain a cross-section of average returns by how much they covary with this entire thing, which is the stochastic discount factor. Right? So the entire content of all of these models is in the stochastic discount factor. That's where the economics is. Okay, so these moment restrictions will form the basis of an empirical investigation. Now, I'm going to call this a semi-parametric model, econometric model, because we have both the finite dimensional parameters, and let's lump these into a vector delta. So we have three finite dimensional parameters, beta, theta, and rho. Beta is subjective time discount factor, theta is coefficient of relative risk aversion, and rho is the elasticity of intertemporal substitution. Okay. So we have a vector of finite dimensional parameters, and then we have an infinite dimensional unknown function, which is this v over c. Okay? So that's a sense in which it's semi-parametric. We've got both of these appearing in the model. All right, so the reason we have to deal with this unknown function is because we do not want to go back to proxying for the aggregate wealth return, because that's also unknown. So we can kind of be in the same position of having to deal with the aggregate wealth return as being an unknown function of stuff. Okay. All right, so what we're in this particular application is say, let's assume that f is a function mapping R2 into R, so that v over c is this function. It's a function of lagged v over c and current consumption growth. Okay. Now, of course, here again, like with GMM, we're going to assume strictly stationary variables. So consumption growth is strictly stationary and ergodic, and this function is such that this v over c process is asymptotically stationary and ergodic. Okay, so then this particular, these arguments would be justified, for example, if log consumption, the change in log consumption or consumption growth is a potentially nonlinear function of a hidden first-order Markov process x. Okay, now, if you wanted to have a second-order Markov process, the proof would probably imply, although I haven't done it, that you need a second lag of v over c here. Right? But what you can show is under fairly general assumptions, if this is true, then the information in this hidden Markov process would be summarized by these two arguments. So if consumption growth has a first-order Markov process, it could be nonlinear, then this says that the continuation value of the future consumption plan divided by consumption growth is some other nonlinear function, right, of v over c and of current consumption growth. Okay, so now the question is, what is f? And we're going to ask the data to tell us what f is. Okay, that's the non-parametric part of this. Okay, we're going to solve for f using the observations we have in our historical sample. Okay. Now just a note here that with a nonlinear Markov process for x, f can display non-monotonicities in both of its arguments. Okay, so we're not necessarily looking for a monotonic relationship between v over c and lagged v over c, and between v over c and consumption growth. Okay, now note that this Markov assumption is only a motivation for the arguments here. Okay. The econometric methodology itself leaves the law of motion for the data unspecified. Okay. But we do have to say what the arguments are of this unknown function. Okay. Now, I would argue that this is not a crazy assumption for aggregate data, at least. Right? That a first-order Markov process is probably a reasonable. The higher order Markov processes are probably not necessary to describe these linear time series process for consumption growth well. Okay, but you want to make more general assumptions, you can, but this is just a motivation for these particular arguments. Okay, but again, this is a methodology that's a distribution-free methodology. Okay, so if we're going to now have ft denote the agent's information set at time t, and let's put z, t plus 1, let's put all the observations at t plus 1 into a vector z. Okay, and then let's now define gamma I to be this thing. What is this again? This whole mess is just what's in the, it's what's in the expectation operator. Okay, that's what we're going to now just call this whole thing gamma I. Notice it depends on I because it depends on the ith asset return. Okay, so that's gamma I. There it is. And then let's call the deltas naught, beta naught, theta naught, rho naught, and f naught true parameter values that uniquely solve the conditional moment restriction. So these are the Euler equations. So with delta naught and f naught, then we know that these Euler equations are exactly satisfied. Let's just use the naughts to denote true parameter values. And let's let W be some observable subset of F. Because again, this might be something the econometrician observes. Right? Now, again, as just as before with GMM. So we have, well, first of all, not as before with GMM. We're going to be, it's a very important distinction here is we're going to be working with conditional moments. We're going to have to approximate this conditional mean. We're not going to be able to turn this into an unconditional moment restriction. And I'll explain why in a moment. That would be what you could do if you want to do GMM, but here we can't do that. So we're going to stick with using conditional moments, and let's let W be some function here. Some subset of F, right? And so now we have these moment restrictions. Okay, so what's the intuition behind this is a C minimum distance procedure. There's a lot of pieces to this going on, but first let's just take the minimum distance part. Okay, because this is slightly different from GMM, although I will show you that this whole thing can be implemented as an instance of GMM. Okay, but so theory implies this, right, that these conditional moments are zero. They must be zero for every observation. So MT, let's call this conditional moment, this conditional mean, zero. Let's call this MT, right? Okay. Now, since MT has to be zero, MT has to have a zero variance and a zero mean. All the moments obviously have to be zero. So we could, in principle, find parameters here. There's parameters in the F and the delta by minimizing the variance or the quadratic mean. So we could think about minimizing this, right, and find parameters. Now, of course, we want to find parameters to make this zero. We don't want to find parameters to make this as small as it could be, because then we'll find parameters that make this negative, right? So we need to square it somehow, right? Something like that. So we could find parameters by minimizing the variance. Of course, we don't observe M here. That's one issue. So we're going to have to estimate M. We're going to have to estimate this conditional mean. But suppose we had an estimate. Plug in M hat. Okay. Now, since this is a conditional mean, it has to hold for each observation T. Right? It has to hold for every observation. Well, how do we deal with all these observations? Well, usually we have more observations than parameters to be estimated. Right? So we need a way to weight each of these observations, and using the sample mean is one way to do that. So what you could think about doing is minimizing. This means sample mean. Right? Minimizing the sample quadratic norm here. Okay, so we're going to think about choosing parameters to minimize the sample quadratic norm. This is a minimum distance procedure, and it's useful for estimating distribution-free estimation involving conditional moments, these conditional means here. Okay, now let's contrast that with GMM. Okay, with GMM is used for unconditional moments. Okay, so at the end of the day, we have got some f of x, comma alpha. Alpha are some parameters, and we're taking an unconditional expectation here. Right, we saw that in the Hansen and Singleton application, we started with a conditional expectation. We turned that into an unconditional moment restriction. That was important. Okay. So you can incorporate conditioning information in that methodology, right, by including instruments. Right? But at the end of the day, your estimation is done on an unconditional moment. And so with GMM, then you have this unconditional moment, you take the sample counterpart, which is the the sample mean, call that G. Then you choose parameters by minimizing this quadratic form. Okay. So with GMM, it's as if you average and then square. So here with minimum distance estimation, we square and then we average. Okay, so slightly different. Okay. So this has a few moving parts, so try to just bear with me a little bit. We have these true parameters we like to estimate. So we have a set of finite dimensional parameters, and we have this unknown function. Okay, again, what is this? This is V over C. So these parameters should solve, again, this is this minimum distance problem, right? This is just this quadratic, this little, what we were talking about here, right? This quadratic norm. Okay? So, but now I've just stacked everything into vectors. So now we have, M is the whole vector of gammas. We have one gamma for each return. Okay? Right? So instead of just putting an I here, I've stacked these into an entire vector. Right? 1 to n, right? There's n of these. Again, this gamma is just what's in the expectation operator. Okay. Now, let's say for any candidate delta, beta, theta, rho, okay, included in some compact set. Let's forget about this V star. That's a typo. We don't need V star. F star. F star is a function of ZT and delta. Okay? Which we'll also just get rid of that Z and have a generic argument. So let's define F star this way. It is the arginf of this quadratic norm. Okay? So F is itself included in sort of the version of a compact set for functions here. Okay? So this would be the arginf. Let's just define it that way, right? So for any delta. Now, it's clear that at the true delta parameter, right, the true delta, then F naught is the same as F star, right? These coincide. Okay, because again, the true parameter value should set this this thing to 0, actually. Okay. So the first step, this is going to be a two-step procedure. In the first step, for any candidate delta, let's estimate this F star. We need an estimate of F star. Okay, and that's obtained using a sieve minimum distance procedure that itself consists of two parts. Okay, the first part is we're going to replace the conditional expectation with a consistent non-parametric estimator. Okay? So what do I mean by the conditional expectation? Again, talking about the conditional expectation in the Euler equation. We'll replace that thing with a consistent non-parametric estimator, which I'll give you an example of in a minute. Second, then we will approximate the unknown function f by a sequence of finite dimensional unknown parameters. These are called sieves. Okay? And they're KT dimensional parameters. So the approximation error will decrease as the dimension increases with the sample size t. So now, we've taken this unknown f and we're just plugging in a known function, but it has to become increasingly complex as the sample size grows. Okay? And then in the second step, we will obtain estimates of the true delta, the finite dimensional parameters, by solving a sample minimum distance problem, such as GMM. Okay. So I'm going to explain why we use these two steps, but let's go back here for 1 second. So first, let's talk about the second part of the first step, okay, which is that we now are going to approximate the unknown function f by a sequence of finite dimensional parameters. All right, so here's b over c. It's a function here. We've already said it's a function of these things, but it's also a function of delta. Okay? So we're going to approximate this with a bivariate c. We have two variables. It's a bivariate c. And we're going to say that f is approximately, let's write this as fkt of delta. This kind of thing. So what does this mean? We have some c coefficients that depend on delta. Here they are. Then we have some basis functions that have known functional forms independent of delta. Here they are. These could be things like B-splines. In fact, that's what we use in our application. Right? Or, I mean, in principle, they could be any number of things. Some things work better than others. Could be polynomials. For this particular thing, the polynomials apparently don't work so well, and they're not shape preserving. You could get into an entire literature on that. But here we use B-splines, okay, like cubic B-splines. Okay, you can see that this function can become arbitrarily general the larger we have kt, right? The more parameters we allow this thing to have. Okay. So then we have, suppose we, you can see what this is. This is vt over ct. It's a function of lag vt over ct. To get this recursive thing started, we need an initial value for v over c. So what we're going to do is just estimate that. Let's denote that v0 over, or v0 over c0. We're going to estimate that. We're going to take that as an unknown scalar parameter to be estimated. Okay, so that's just another parameter to be estimated in this model. We're going to be estimating a bunch of parameters involved in just this c alone, right? That's going to be one of them. The other one's going to be all these a's, right? A bunch of a's. Now, if you are given, if I give you a v0 over c0 to start, well, you're going to estimate. These are the parameters we're going to be estimating, right? These two. Now, these are known basis functions. But given this, and this known basis function, if we have data on consumption, we can use the data on consumption. We can use fkt to generate a sequence of observable v over c's. So now it's as if we have data on v over c. Okay? Imagine you start out with some initial v0, v0 over c0. You put that in here. Right? You put in your initial consumption observation. You pick some initial values for a. You have a known basis function over that. You now have next period's v over c. You plug that back in. Continue like that. Okay, so now we've generated an actual time series on the v over c's. Okay, and just recall that m is our conditional moment restriction itself. And we've defined it this way. That has to equal 0. Now the first step, c of minimum distance estimated of f hat, is therefore going to be based on the sample analog to the population minimum distance problem. Okay, so here I've substituted the sample mean. And now we're just taking the argmin, so go back. This fkt is now a parametric function in practice, right? We've turned this unknown function into just another parametric function. It's a complicated one, and if you have enough observations, it should be highly dimensional in order to capture potentially highly nonlinear aspects of this function that we don't know. We're trying to figure out what it looks like, right? But now we have a parametric function, and we're going to choose the parameters, those alphas, and that initial value in order to minimize this quadratic norm. Okay? Now, I put hats here because we need an estimate of the m, and I haven't told you how we're doing that yet, but assume we have that estimate. Okay? This is going to be a non-parametric estimator of m. So we have so not to confuse, there's two non-parametric parts to this. One is the unknown f function, and then the other is we don't know the conditional mean. We have to come up with a non-parametric estimator of that. Okay. So we have that, then we can compute this. And we're going to do this argmin minimization for a three-dimensional grid of values, beta, theta, and rho. So a whole bunch of different beta, thetas, and rhos combinations. Okay, we're going to do that. All right, so this is estimate of F star. Remember, F star is just, we choose the F to minimize this for any value of delta. Okay, so here's an example of a non-parametric estimator of M. We need an M hat. We're going from M to M hat. Let's take, let's call these J basis functions of known conditioning variables. These are functions mapping a dimension of W into R. Let's call those instruments. So suppose I have a single instrument. Okay, let's call it X. These are functions of that instrument. Okay, in practice, here you can use almost anything. But for example, polynomials, you might use x, x squared, x cubed, x fourth, and so on. If you have x and y, you could use x times y, x and y alone, x squared and y squared, x times y squared and cubed, and so on. You can use polynomials. So these are basis functions of known conditioning variables. And let's just stack all those functions into a vector here. And then we can define this big, huge P matrix, which is take all those functions and stack them for every time period, right? So this is now T by J. So now we're just stacking known basis functions of some conditioning variables, and we're calling those known basis functions instruments. Okay? Then this is a sieve least squares estimator of M. What does this mean? This procedure is equivalent to regressing each of the gammas. Gamma is what's inside the conditional expectation operator, right? It's all that stuff. It's the stochastic discount factor times the gross return minus 1, okay? It's all that stuff. You take that gamma, regress it on the instruments, and take the fitted values as an estimate of the conditional mean. That's what this is equivalent to. This would be a sieve least squares estimator of the conditional mean. Now, just like as before, as you let JT go to the infinity, you're getting an arbitrarily good estimate of the conditional mean. Okay? That's what the theory would suggest. Okay, so that's what this just says. Take these gammas, regress them on basis functions of known conditioning variables, take the fitted value out. Now is your estimate of the conditional mean. So now we have an M hat, essentially. Now, an attractive feature of this estimator of the F star, we haven't gotten into the second stage yet, but attractive feature of this estimator is that it can be implemented as an instance of GMM. So YT is all the observations that we have, right? Stack them all here. These are the conditioning variables that we're forming basis functions over, right? And these are all the like consumption and returns and so on, right? And GT, these are our sample moments that we would do GMM on. Notice that this is just like, this is exactly like what you would do in GMM. You have some instruments, and you're chronicling that with each of the arguments of each of the expectation. Right? This is exactly what we had with Hansen and Singleton. The only difference is now you have basis functions of of conditioning variables as instruments. Okay, don't just throw the W in by itself. So that's all the same. The difference is in this weighting matrix here, you have to use a specific weighting matrix. Okay, now what is this? It's just the identity chronicled by P prime P. So these are this matrix of instruments, basis functions of known conditioning variables. Now this weighting gives greater weight to the moments that are more highly correlated with the instruments. Why is that important? It's important because it can be understood intuitively by noting that variation in the conditional mean is what identifies the unknown f function. If you have no variation in the conditional mean, you can't identify the function. This is also why we have to work with conditional means here. We can't just go the GMM route, because we're not going to be able to identify the function. When you think of the f function is in here, right? And so we sort of think about if you could invert the moment condition to get back to the f function, you'd be able to identify the f function. Of course, the moment has to move around, so you can't have an unconditional mean. So that is why this weighting gives greater weight to moments that are more highly correlated with the instruments. Okay. You want to get a lot of variation in the conditional mean in order to identify this f. Now, if the model is literally true and under the true parameters, then we should have these moment conditions are exactly satisfied. Okay, so these are now, okay, step back. So now we have our F star. We've got an estimate of F star, which we're calling F hat. But given this, if the model is true, we could always take any subset of information, put it here, and take an expectation that should be 0. So now we're coming into talking about the second step, estimation of this delta naught. So we could then form sample moments of this thing, right? So here's some other x here. Okay, I'm sorry if this is confusing. There's two types of conditioning. The conditioning that we're talking about here, these p's, right? That's to estimate m hat. Okay, and we need m hat in order to estimate f, the first step. Okay, now we're going on to talk about estimating delta. Okay, and now we don't need the p's anymore. This is an unconditional moment restriction. This also has to be true if the model is true. Now we can work with unconditional moment restrictions because suppose we know what f is. We don't have this problem of estimating an unknown function. Okay. Well, sample moments would just be given by this, right? This is again just like a GMM sample moment with instruments, right? Except for now we're going to plug in our estimate f hat for a given delta here. Okay, plug that in. I put that in red to emphasize that. Now, regardless of whether the model is correctly specified or not, in this procedure we're going to estimate delta by minimizing the GMM function. What do I mean by correctly specified or not? Suppose that you can't make the Euler equations 0, right? Because the model is misspecified. So that's okay. Then we're going to be estimating so-called pseudo-true parameters by making the Euler equation as small as possible and choosing the delta to be as small as possible, even if it's not 0. We want to allow for that because it gets back to this theme of, all of these models, in fact, are misspecified. We shouldn't expect them to hold exactly correctly. And the question is, which are least misspecified? That's the interesting question. Okay, so regardless of whether these Euler equations are hold identically equal to 0 or not, we're going to still estimate delta by minimizing a GMM objective function here. This is our G. We plug in our f hat. Okay, we've estimated f hat in the first stage. So we now proceed like with GMM. This f hat is no longer unknown. So we could just do GMM. Examples for the weighting matrix could be anything like identity or the inverse of the second moment matrix for returns as Hansen, Jaganathan recommend. Again, we're not going to get any kind of efficiency here, but these would be reasonable examples of matrices. I'll talk about why to choose some of these in a second, well, especially this one. Notice here, though, that f hat is not held fixed in this step. It varies with delta. All right, so every time we change delta, we go to a new f hat. That's because we already solved f hat for a whole grid of deltas. So we could just change it. We already know. We have many, many f hats depending on delta. Okay. And this estimator f hat is obtained using minimum distance over a grid of values for delta. That's what I just said. So let's choose delta, and then, of course, the corresponding f hat to minimize this GMM criterion. Okay, so now we have an estimate of delta and f hat. Okay. Of course, once we have delta and f hat, we have an estimate of the stochastic discount factor. Now, you might ask yourself, well, why should we be estimating this in 2 steps? I mean, after all, we could estimate all the parameters in one step by minimizing the SMD criterion. So let's go way back here and look at this thing here. Instead of just do argmin FKT, where meaning pick all those A's here, right? We could also pick the beta theta rho here. Do that in one step. Okay. Well, so we would argue this for asset pricing, this can be less desirable. At least for the applications that people are often interested in. Why? Because, for example, we might want estimates of the coefficient of relative risk aversion and the elasticity of intertemporal substitution to reflect values that are required to match unconditional risk premium. Okay, like, at the equity risk premium, for example. This wouldn't be possible if we use the SMD criterion to choose beta, theta, rho, because that criterion emphasizes conditional moments, right? So this is, think back to the beginning of the lecture where we said that, Hansen and Singleton didn't have an equity premium puzzle. They didn't need to estimate a higher gamma because, in fact, they were no longer looking at the equity premium. They were looking at equity returns times some conditioning variables, and so those became a totally different set of returns. Suppose you want to take this model and say, well, how well does it explain a particular set of returns? So in finance, people are very concerned, for example, with the value premium. Okay, you take portfolio returns, sort them on the basis of book-to-market ratios, and it turns out that portfolios with high book-to-market ratios have really high average returns, and those with low book-to-market ratios have really low average returns. Right? And the CAPM and mini models can't explain that spread. And you might like to know, well, does this model explain that spread? Or if it does, how high does risk aversion have to be, and so on, right? But you would not be able to answer that question if you would estimate beta, theta, rho using the seed minimum distance criterion, because you no longer would be looking at those portfolio returns. Okay. So it's the same thing that happened to Hansen and Singleton when they were no longer looking at the equity premium, right? They estimated a low gamma. And I suppose this just gets to, one of the places where judgment and purpose about what you're doing really comes to play, because, in finite samples, especially if results depend on the moments you choose to match, to estimate the parameters under. All right. The other thing is that the seed minimum distance procedure, and this is what I just said, this effectively changes a set of test assets. So now you're back using linear combinations of the original portfolio returns when you pick parameters to minimize that seed minimum distance criterion. We may be interested in explaining those original returns, so we're undoing all of that. Okay? And again, as I said before, these linear combinations may imply implausible long and short positions in the original test assets. And they may not give you a large spread in average mean returns across assets. So again, there's not much for the model to estimate. Now you have to estimate the seed parameters, of course. You have to estimate the unknown function with the seed minimum distance criterion because you can't identify it otherwise. Right? So that has to be done. But here, for these other parameters, you don't have to. All right, so this procedure allows for misspecification since the Euler equation doesn't need to hold with equality. Okay, we're just going to estimate, in that case, pseudo-true parameters. Whatever parameters make the Euler equation as small as possible. The error as small as possible. And as before, I just want to emphasize, you could then compare models. Suppose you had this Epstein-Zinn model, you might have a couple other models. This is one of the things we did, by the relative magnitude of misspecification, rather than asking whether each model individually fits perfectly given sampling error. So to do that, you would just use W equal G inverse in the second stage GMM, and you compute the HJ distances for a bunch of models, for this one, and a bunch of models, and you could compare models. That's another reason to do this two-step procedure, because you have a way of assessing model misspecification and comparing it to misspecification of other models. And again, you can just test whether these HJ distances of competing models are statistically different. Okay. So this is different. This is different from testing whether the HJ distance itself is different from zero. We say don't even bother testing that. It shouldn't be exactly zero, because I don't really believe this model is a complete description of the data. But maybe it's not as maybe comparing the Epstein-Zinn model with the standard constant relative risk aversion case, where you restrict the coefficient of relative risk aversion to be the inverse of the EIS. Maybe it does better than that. And that's useful to know. Okay, so the last thing I want to talk about in terms of estimating these models, and again, the goal here is let's try to be as general as possible. Let's not, if we can, let's not estimate things let's not use estimation techniques that rely on assumptions like the EIS is approximately 1 or everything is jointly log normal, because we might not believe those restrictions are true. So this is another methodology that, if theory provides more guidance or restricts the law of motion for some of the underlying variables, then you can use simulation methods to get around the fact that this continuation value is unobserved. Okay, so this is an example of that. This is published. Bonsall, Galant, and Tauchen are estimating, this is sort of a simulated method of moments estimator of this long-run risk model of Bonsall and Euler. All right, so this is restricting to specific law of motion for cash flows, so-called long-run risk law of motion. There's also going to be some stochastic volatility in here too. Okay. So this is the Bonsall, Galant, and Tauchen version of the long-run risk model. Now this is slightly different from the original Bonsall. Bonsall-Yaron model, and I'll explain where it differs. But here we have, these are again lowercase letters or log variables, so we have consumption growth equal to some constant mean times a component xt, lagged, plus a shock that has a time-varying standard deviation. Okay? Now this xt, or xct, is an AR1 process. And in the Bonsall-Yaron model, this is calibrated to be, so in the Bonsall-Yaron model, it's nothing's estimated, right? They pick some parameters to match certain things of the data, right? And then they solve the model and see how well it does just, by matching things, by matching moments. I mean, nothing statistically, no statistical comparison of model moments and actual moments, just, presenting moments. This is calibration. So they calibrate this theta to be, this phi to be very high, so that you have this persistent component. Now this shock here might have a small variance. You could control that here. Wonder if this should have a T on it actually. I'm drawing a bit of a blank, but this might have to have a T. I might have forgotten to put the T. We'll have to check that. But in any case, this thing could have a small variance on average, and then they calibrated it like that, right? So they wanted this, so the sigma epsilon x was really small. So there was this idea that you have this small but very persistent component in consumption growth. Why does it have to be small? Because if you actually look at consumption growth, it doesn't seem that it's that persistent. I mean, there's some serial correlation in it, but it doesn't seem like it's that persistent. So you don't want this to be a huge part of the variability in consumption. So you want this to have a small, but if it's very persistent, it can have important asset pricing effects in models with these kind of recursive preferences, where the timing of the resolution of uncertainty really matters. So, if you have cash flows that have small variance over short horizons, but the variance grows with the horizon over which it's measured, the annualized variance, this could make a huge difference in a model with epsilons in preferences, even though it doesn't make any difference in a model that's a special case of that, where rho is equal to gamma inverse or theta inverse. Okay, so that's how they calibrated it, and this is what we call long-run risk, right? Long-run risk, and actually, in this model, dividends and consumption are two different things because they don't want to make the equity return be a claim to future consumption. So dividends are sort of a levered up version of future consumption. Okay, so this part of the consumption risk, though, gets into the dividend. So they've just specified a dividend process that looks like this. All right, so this is, very similar. You've got this is like a quote-unquote leverage parameter where they expect to be greater than 1. Right? Because dividends are a lot more volatile than consumption. Of course, here we're just going to estimate all these parameters. We're not going to calibrate anything. Now, what is this S? Okay, in this particular version of the model, S is a co-integrating residual for log dividends and log consumption. And notice that the co-integrating coefficient here has been imposed to be 1, -1. Okay, because S is a stationary variable. Right, but D and C are not stationary. The linear combination of log D minus log C is stationary. So S is a stationary variable. And this is a way to write a co-integrated system in which a restriction has been imposed that the lagged, this is like a vector error correction representation where the restriction has been imposed that the lagged co-integrating residual does not affect one of the two variables in the system. Of course, it has to affect at least one of the variables in the system, otherwise the variables aren't co-integrated. But here, it's not affecting consumption growth, just dividend growth. Okay, so that's another restriction that they're imposing. They're just imposing this. This was not actually part of Bonsall-Uren's original model. They actually didn't have any co-integration between consumption and dividends. Okay, but here they impose that. I was just talking to Wayne Ferguson, and he's doing some estimation of these models under some simplifying restrictions, but also imposing or not imposing co-integration, and finding that imposing co-integration allows the models to fit to be negative. In practice, I guess they don't find it's ever negative given their parameter estimates. But in general, that could be a concern. And, there might be various ways to try to deal with that. In their sample, they don't find that it ever goes negative in any of their estimates. And then the other thing that's imposed here is that all of these shocks, 1, 2, 3, 4, are normal IID variables. Okay, so here we're putting a lot of structure on the law of motion for the data. That's different from the previous methodology, where we left those unrestricted. But here the model is implying this kind of structure. Well, in particular, the long-run risk piece. All right, that's very important to the structure. Okay, so this is C minimum distance method. What am I saying? This is a simulated method of moments procedure. And the background, important background for this work is in Gallant and Tauchen. This is this classic paper about which moments to match. Gallant, C and Tauchen, and Tauchen have good survey papers as well. And Tauchen is a survey paper. These were very useful to me in understanding this approach. Okay, so here's an outline of the steps here. You have this model. Okay, no, I should have said, combine this cash flow specification, this whole thing, with the Epstein-Zinn recursive utility. So that's always still there. Exactly the EZW stuff that we talked about, that's the same for this model. Beta, theta, rho are still the structural parameters of that utility function. Okay? You're just now superimposing on that this set of this law of motion for the data. Okay, so you solve that model, right, independent of the data. You solve the model. You have some way of solving it. There are various ways you can solve it. If you're going to do long simulations of the data, as we will be doing here in this procedure, you could solve it using the long simulations. You can actually. This model is close to log linear, so you could actually take log linear approximations of everything and do an approximate analytical solution. That works very well, too. But in any case, you have a way to solve the model. Okay, now that you've solved the model over a grid of values of these deep parameters, let's call those deep parameters rho D. This is the beta, theta, rho from the Epstein-Zinn utility function, and all of these other parameters from here. Right, all of these guys, the mu's and the phi's and the so on. Okay. Notice that in the model, of course, the V, the continuation value of the future consumption plan, is completely observed. You can solve the model, you can see what that is, right? It's the fact that in the data we don't know what that is, right? But within the model we know what that is. So there's no question of that being unobserved. So we solve it for some grid of parameters, and there's quite a few parameters here. Then for each value of rho on this multi-dimension grid, let's combine the solutions of the model with a long simulation of the model of length n. Now, given modern computing technology, you can compute very long simulations, which is good because this methodology really, to get consistency, you really need big N. So simulate for a long simulation, just once for each value of each rho D that you choose. Okay? So this means take Monte Carlo draws from the normal distribution, right, for these shocks, and compute the simulated implicit values of the endogenous variables. And then you're going to, right, so that's what you're going to do here. You're going to form what's called an observation equation for the simulated and the historical data. Okay, so here in this Bonsall, Gallant, and Tauken, they used an observation equation that consisted of, there's some judgment as to what to put in here, right? They chose variables that they felt were useful for summarizing the main asset pricing implications of the model. So these would be things like the dividend consumption ratio, which is presumed to be stationary, consumption growth itself, the price dividend ratio, and RD is the log return on the claim to dividends, or an equity return. Okay. But I mean, in principle, you could choose anything here. But it's going to be this, you can form a set of observations for the simulated and the historical data. And then you're going to choose which row, based on which row most closely matches moments between the distribution of the simulated data for these variables and the historical data for these variables. And by match, I'll make that precise in just a minute. And that's the basic idea. So here's how it works. You have y hat. Let's let this be, remember that we have simulations of length n from the model. So let's y hat, let's let that be a simulation, a realized simulation from the model. Of course, this will all be conditional on whatever row D you chose. You have a bunch of these, grid of these y hats. And then let's let y tilde be the historical data on those very same variables. So now the tildes mean historical data and the hats mean simulated data. Okay, now this is, you have a t here. This is the length of our sample on historical data. And then we're going to define an auxiliary model of the historical data, right, for that y. For example, it could be a VAR. That would be a simple one. In fact, I think that's what they ended up using, although they started with some other nonlinear variants. I'm not sure what. But I understand from George that they experimented with other variants. But suppose it's a VAR, for example, it'll have some density. Whatever it is, it's going to have a density. The data will have a density, and it'll depend on some parameters here. Okay? Now, if this is a VAR, and this density, these parameters alpha are going to be the coefficients on lagged endogenous variables and the elements of the error covariance matrix. Right? So these would be VAR parameters. Right? Think of it as a VAR for simplicity. In any case, it should be a good law of motion for the data. So they say you should be doing specification tests at this point based on something like Bayes information criterion to choose this. If a VAR works, or if you're restricting to VAR, linear models is at least specification tests on the number of lags and so on. But if you think of generalizations of VAR that are nonlinear, you probably should include those as well. So, but this is what we call an auxiliary model. It should be a good law of motion for the data, and this is, let's call this an F model. They call it an F model for short. Okay? Now, there's a score function for the F model because, again, this has a density, right? The score function is just the derivative of the log of this density. Okay, let's call this a score. This is to define S of F this way. Okay? Now, what is this density, in fact? Well, in practice, they use the normal density. In principle, you don't restrict yourself to normal, and you can also try departures from normality. And one way to do that is to use Hermite polynomial expansions around the normal. This involves more parameters, of course. But you could ask whether the methodology worked better using non-normal distributions here. In the end, they ended up just using the normal. Okay? So let's think about that as the normal density, and this is the score function for the F model. So here we're still just talking about the historical data. The quasi-MLE estimator of the auxiliary model on historical data is just the, what we always do for MLE. Just pick theta hat, or excuse me, alpha tilde, right, as the argmax of the log likelihood function. So what is this? This is the log likelihood function. Again, this is just historical data. So, right, this is VAR. These are your lagged VAR coefficients and the elements of the error covariance matrix. You're just picking them to maximize the log likelihood function for the historical data. Okay. So the first order condition here for this MLE optimization is just, you set the derivative of the log likelihood to 0, which is the same as saying that the average of the scores should be 0. This is just MLE first order condition. Okay. This cap T means the in-sample, the sample variant, right? So we have a sample mean here. You could have L lags. That's why I'm going from L plus 1 to T. Now, here's the idea. So since this is true, right? So since in the regular historical data, this first order condition should hold, which means the average of the score should be 0, then a good estimator for rho D, which is the structural parameters of the underlying model, would be one that sets this thing to 0. Now notice what's happened here. Instead of T, we have N. Right? So we're now taking averages over one long simulation instead of, but what we're doing is we're using the score function from the data of the density of the data. We're using the parameter estimates of the density for the data, but we're plugging in the simulated data from the model. And of course, that depends on rho, right? Because for each rho, you get a different simulated set of y's. So you could see how you could choose rho to make this approximately 0. That's the recommendation. That's the instruction. Choose rho to set this to be approximately 0. Now, this thing has dimensionality equal to alpha, right? So if alpha were equal to this, exactly equal to the dimensionality of rho, you could, again, with the same number of equations as unknowns, you could just solve each one, assuming there is a solution, right? Because again, we have nonlinear equations here, these scores. But if these are a set of moment restrictions, it's like a GMM again, right? This is just a set of unconditional means that we want to set to 0. There's alpha of them, dimension alpha, right? So if alpha, the number of moment restrictions, is greater than the dimensionality of rho, you can use GMM, right? So let's let M hat be this thing. It's dimension alpha by 1, and the GMM estimator would be this, right? So typically, you have a rich F model or auxiliary model, and you're going to have, therefore, more moment conditions than parameters to be estimated. And so you're going to have, these would be your sample moment restrictions, and the GMM estimator is just this. Pick rho D to minimize this thing. And this is just quadratic form. Just like, so ultimately this is a GMM estimator of rho D. Okay? Now, what is this weighting matrix here? Here I just repeat that from above. This thing is the inverse of the variance of the scores. So it's an information matrix. But it's data determined from the F model. So this is what this is. Okay? It's all data determined from the F model. Historical data estimates, parameter estimates. Right? That's what that is. Okay? Now, the simulated data, of course, will follow their own density. Right, let's call that P. Here, P of the joint density of all these lags. These are the observation equation. That depends on rho. Note that there's no closed form for that. Right? We don't know what that is. Because these are functions of the endogenous variables of a nonlinear model. Turns out we don't need to know that, thank goodness. And the intuition for this estimator is that, recall that we have this M hat, which is the sample moment restriction that we're trying to set to 0 in GMM, and we're choosing these parameters. That converges almost surely to M as n goes to infinity. This is why it's important to have large simulation length. As n goes to infinity, that converges to this. Now, what is this? This just says we're using the Monte Carlo simulations to compute expectations of the scores under the P distribution. That's what this is, the expectation of S under P. Okay, so that's what I'm repeating here. Expectation of S and repeat. Use the Monte Carlo to compute the expectation of anything we want under P. This is the general result. Okay? Now, if F really were equal to P, if the data generating density were the same as that for historical data were the same as that for simulated data, then what this would be is the mean of the scores of the likelihood. That, of course, should be 0, given the first order condition for MLE. And that is exactly what we're trying to set to 0. Right? So that's why this kind of makes sense. So if the data actually do follow the structural model P, then this thing should be 0. And this also could form the basis of a specification test. So this gives you the logic behind these particular moments. All right, this is a GMM estimation. The moments are these scores, score functions, right? And here they are. The moments are these score functions, which depend on rho, score functions of simulated data, where the score is coming from the historical data. Okay. And is dependent on the parameters of the historical data estimates. All right, so they also talk about how you can do a specification test based on this. Again, now keep in mind that the specification test is like the test of Hansen's OID restrictions. It's asking, is this model literally true? Are these things exactly 0, these moments? That's what the test is. Whereas I've been arguing that maybe the more interesting thing is not whether these things are on their own 0, but whether they're less far from 0 than some other model that we might be interested in. Nevertheless, many people want to compute these tests. So, summary here, so you're going to solve the model many times for many values of rho. Each time you do that, you're going to store long simulations of the model for these observation equation and variables, right? Store those. Then you do a one-time estimation of the auxiliary model, just once. And then you're going to choose rho D to minimize that GMM criterion, all of which can now be computed from your single estimation on historical data and using all of the various simulated variants of your model based on different values of this rho. You can see how this, it's a messy problem because you have a lot of variables here in rho D. There's a lot of things to store. But, technology marches on and we can do this more and more as we go through time. Advantages of using these score functions as moments. The simulated method of moments, you don't have to, the question is what moments should you be matching here? And the recommendation here is match the scores. Why is that a recommendation, or why is that advantageous? Well, one is simply computational. And you just have to do this one-time estimation of the structural model. Now, this is very useful if F is a nonlinear model. Here, we've been thinking about a VAR, and in fact, in their application, that's what they ended up using. So, in that case, there's not much computational advantage because a VAR can be estimated many times very, very quickly. But if it's a nonlinear model and you're searching over parameters, this is a huge computational advantage. And you think of, one of the contemporaneous papers in this literature that was dealing with simulated method of moments is a paper by Tony Smith. And in that particular application, you had to estimate the structural model every time you changed the parameters of rho D. So it was a different procedure where you're actually matching on the VAR coefficients of the structural model and the historical data. And instead of, let's see if I can remember how this works. Here, right? So here, what are we doing? We're taking and fixing the parameters of the auxiliary model at their estimated historical value, and then we just keep plugging in different values of y hat as rho changes, right? What that does is to say, no, let's every time we change rho hat, let's use the it won't be the score function, but it will be the density of we will recompute the density of the historical data based on different values of rho hat. So that's probably not very clear. But in any case, in Tony Smith's method, you have to keep re-estimating the auxiliary model every time. Okay? Every time you change the parameters of rho. So that could be computationally very burdensome. So this is a huge advantage if you have a nonlinear auxiliary model. If the F model is a good description of the data, as we want it to be, then at least under the null, the MLE, you'd have MLE efficiency. Okay. So that's another reason to use these particular moments. Now, if the dimensionality of alpha, so if the number of moment conditions is greater than the number of parameters that you're estimating, then these score-based sieve minimum, I'm going crazy up here. Simulated method of moments are consistent and asymptotically normal. Of course, assuming, and this is the big assumption that we almost always make, that the auxiliary model, here in this case, it's the auxiliary model, is rich enough to identify the nonlinear structural model. Now, sufficient conditions for identification are unknown. This is just a counting rule. Right? So this is an order condition. There's, of course, a rank condition implied in the background. And sufficient conditions for those to be satisfied, I don't think, are known. Well, I asked George Tapkin, and he wasn't clear on what they were, but was, I mean, it's always a problem in nonlinear models, not necessarily specific to this particular case. So essentially, we have to assume identification in order to get these asymptotic results, consistency and asymptotic normality. Now, of course, if you're doing this in practice, the sign of not having an auxiliary model that's not rich enough to identify the data would be very large standard errors in parameters. So you'd have some hint. Okay? You'd have trouble identifying these parameters. You expect very large standard errors. The big issue here is, are these the economically interesting moments? So a lot of arguing goes on among the authors of these paper and other people in asset pricing about, sure, we're choosing these moments, these scores, and then we're weighting them in a particular way for statistical efficiency. But as we do that, again, as we've talked about, we're undoing the carefully chosen set of characteristics that we originally chose these test assets to match. And so this regards both the choice of moments and the weighting function, again, as we've spoken about. So using this way, maybe you're not asking the model whether it can explain the value premium, for example. An econometrician might say, well, maybe that's the wrong question to be asking because you're just hiding this specification in other ways, right? We need to give more weight to the statistically most informative set of moments. Okay, this may not coincide with the economically most interesting moments. Okay, so that's a big, I think, unresolved issue. There's nothing that can ever resolve that, actually, other than the discussion goes on. All right, so here are my concluding thoughts about this. There's been a small and slightly growing body of work that's linked financial markets to macroeconomic risks. And these would be given by the primitives in the intertemporal marginal rate of substitution over some numeric consumption good. Of course, you could have other elements of the utility function, not just consumption, but we saw housing as an example. Right? But there's always a numeric consumption good, and that's going to be in there, along with potentially other arguments like habits or housing or something. No model that relates returns to other asset returns can actually explain asset prices in terms of primitive economic shocks. So these models are only descriptive, right, even though they fit very well. And so that motivates us to study these consumption-based models. Right? And so far, many of these consumption-based models have been evaluated using calibration exercises. And we talked a little bit about the Bonzal-Yaron example of that. But of course, a crucial next step, and that's a great place to start, but a crucial next step in evaluating these models is structural econometric estimation of the models. So I tried to cover a couple ways that we've tried to get started with that in the most general circumstances, but a lot more work can be done in this area. However, these models are imperfect. They're never going to fit the data infallibly. And I have argued here for a need to move away from testing if models are true, literally, because they're not, towards a comparison of models that are based on the magnitude of misspecification. And I've tried to suggest one way in which you could actually do that statistically. And an example is the scaled consumption models. So, rather than ask whether the scaled models are literally true, we could ask, for example, whether allowing for state dependency on consumption growth in the stochastic discount factor reduces misspecification over the analogous non-state dependent model, which would be the classic consumption CAPM. Okay, and macro data, are especially troublesome in some cases because they're, unlike financial data, measure with potentially a lot of error. So we can't really expect these models to perform as well as financial factor models of the stochastic discount factor. I mean, one way to think about this, the true systematic risk factors are macroeconomic in nature. If you buy that, and the asset prices are derived endogenously from those, then the financial factors that work really well in explaining, or rather in describing returns statistically, these could represent the projection of the true M, which is a function of macro variables or consumption variables, say, onto portfolios. So these would be what we would call mimicking portfolios. Right? But if that's the case, then they will always perform at least as well or better than, if they're better measured, the financial factors, than these mismeasured macro factors from the true M. Right? So then it doesn't seem sensible to run horse races between financial factor models and macro models. So the goal here is not to find better factors than the financial factor models, but actually to try to explain the financial factors from deeper economic models. So I'm happy to